Hi, this is Chapter 3, Section 7, Changes of State. So the different states of matter, which we learned about previously, are solid, liquid, and gas. And one of the things that we learned about them is that they're really associated with different sort of average energies for the particles involved in the matter that you're talking about. So solids, for instance, have the least energy per particle, and that's why the particles are sort of locked into their fixed positions. Liquids have a little bit more energy, so they're able to move past one another. And then gases have the most energy, and the particles in a gas just fly around completely separate from one another. So when we put heat into a substance or we take heat out of a substance, if you add heat, you increase the temperature. If you remove heat, you decrease the temperature. We learned all about that when we were talking about specific heat. But that assumes that the substance stays within one phase or one state of matter. But there are times when you heat something up so much that you begin to change the phase of the matter, right? So you can take liquid water, and if you add a little bit of heat to it, you just warm up the water. But if you add enough heat to it, you'll bring it to the point where it starts to boil and convert into steam. So it takes heat to increase the temperature of the water to its boiling point, but then it also takes additional heat to break the liquid water up into the gaseous state. Okay? And that occurs without a change in temperature. So when you're putting energy in to a change of state, the temperature remains constant. Okay? It's a very important thing to remember about changes of state. Okay? So the first change of state that we're going to talk about is melting and freezing. Melting and freezing are the reverse processes of one another. Okay, a solid melts into liquid, and then the liquid can freeze back into the solid. So melting occurs when the atoms or molecules in the solid gain enough energy to break away from their fixed positions, right? And that converts them into the liquid phase. They're still close together, but they're able to move relative to one another. Freezing is the opposite. Freezing occurs when the molecules lose energy and therefore become fixed in place and they turn into a solid. Okay? The process of melting or freezing can be described by the heat of fusion. Okay? Again, the heat, typically when we put heat into a substance, the temperature will increase or decrease. But if we're talking about during a phase change, the heat goes in and doesn't change the temperature, it changes the phase instead. Okay? So the heat of fusion is an energy associated with either freezing 1 gram of a liquid, right? So 1 gram of liquid freezing will release a certain amount of energy, or the same heat will be absorbed by 1 gram of the solid to turn back into the liquid at its melting point. Okay? So again, going from a liquid to a solid, the system needs to lose energy, so heat will be released. Going from a solid to a liquid, you need to heat it up, you need to put energy into it, and so it absorbs energy. But if you're talking about the same mass, a gram of the liquid or the gram of the solid, then it's the same energy regardless of which direction you're going, right? It's the same energy released when you freeze as is absorbed when you thaw or melt, okay? So we can write this as a formula. The heat of fusion can be written as the heat absorbed divided by the mass of the substance absorbing it, okay? So this means that if we have a certain mass of, say, ice, then we're going to need a certain heat, a certain amount of energy or heat energy to melt it. Okay? The ratio between the two is the heat of fusion. And so what is the heat of fusion? Well, it's different for different substances, right? A pure substance is going to have its own heat of fusion. So to give you an example, for water, which is a common one that we'll encounter, water has a heat of fusion of 80 calories per gram. That's what you see right here. Okay, so what that means is that if you have ice, right, in other words, solid H2O, we haven't really looked at chemical equations like this yet, but this is the formula for water, H2O, and the S here indicates that it's a solid, right, and solid water is just called ice. So if we take a certain amount of ice and we add 80 calories for every gram of ice that we have, then it's going to convert, it's going to change, that's what the arrow indicates, it's going to change into the same mass of liquid water, okay? And it's going to do this at a constant temperature, okay? Remember, there's no temperature change associated with the phase change, so all of the heat goes into converting the ice into water. right? And it's the same going in the opposite direction. So if we have a certain amount of liquid water, right, that's what the L stands for, then this can be converted into ice or solid water by releasing the same amount, 80 calories per gram, okay? So here you're taking the ice and you're adding the heat. Here you're taking the liquid and you're subtracting the heat. So you can think about it as H2O liquid minus 80 calories. But in chemical equations like this, we never put subtracting a product or subtracting a component or subtracting an energy. Instead, we would move it to the other side, and that's why it becomes 80 plus 80 calories per gram. Okay. So in other words, the 80 calories here was originally, the 80 calories here was originally in the liquid water, and when the liquid water froze into ice, that 80 calories was released into the environment. Okay. So we can think of this heat of fusion as a conversion factor, right? It relates the mass of water to the amount of energy needed to freeze it, or the mass of ice to the amount of energy needed to thaw it or melt it. Okay? So 80 calories for every 1 gram. If you have 2 grams, you need twice as much, or 160 calories. If you have 3 grams, you need 3 times as much, or 240 calories. Okay? And then we can also see here it's the same property is written in terms of joules. So 80 calories equals 334 joules. So this is the same heat of fusion for water or ice in a different unit. So how do we use that? Well, this is an example of a problem you might get. Okay? Very simply, how many joules are needed to melt 32.0 grams of ice at 0 degrees Celsius? Now remember, during a phase change, there is no temperature change. All of the heat goes into changing the phase, right? It's either released in order to go from liquid to solid, or it's absorbed in order to go from solid to liquid. So there's no temperature change. This temperature is really an extraneous or unnecessary piece of information. They just give it to you for context, but you should know that if you're melting ice, well, the melting point for ice is 0 degrees Celsius. It's the same as the freezing point for ice. It's just going in the other direction. So we don't need this. The only thing that we need is the mass of the ice and the relationship between the mass and the amount of energy needed. Okay? And so that relationship is given by the heat of fusion. So in a sense, there's 2 different ways that we can do this problem. We can look at the original heat of fusion equation, right? Heat of fusion equals heat divided by mass, and we can put in the heat of fusion and the mass and solve for the heat, or we can look at this as a conversion factor and start with some mass, right? And then multiply it by the heat of fusion, which is really going to be calories per gram, and then that's going to give us our answer in calories, right? Because the mass unit would cancel grams, and we'd be left with calories. So let's go through step by step, right? We know that we were given that we have 32 grams of ice, right, at 0 degrees Celsius. Again, the 0 degrees Celsius is not necessary for the math, at least for this problem. And what we want is the number of joules, or the amount of heat in joules that melts this amount of ice. Okay? So we have to remember that the connection between the mass of something that we have and the amount of energy it takes to change its state is called, in this case, the heat of fusion. Right? We'll see other heats for other processes like evaporation or condensation. Okay? But now we're dealing with fusion, which is another word for solidifying, right? Liquid solidifying, or it's the opposite of melting. So if we want to write a plan to convert the given quantity to the needed quantity, well, we start with grams of H2O, and then it's the heat of fusion that provides a connection to the number of joules. Okay? So the way that they suggest you do it is to write the heat as a conversion factor, right? Again, it's a conversion factor that relates mass to energy. So 1 gram of water, the mass, in this case it's ice actually, solid, requires 334 joules, or corresponds to 334 joules of energy. So we can write it as these 2 conversion factors. Which one we use is going to depend, right? But we're starting with the mass. We know that we have 32 grams of water. So if we're starting with a mass unit, then when we multiply it by this conversion factor, we're going to want the mass unit to be in the denominator to cancel out. This grams is going to cancel this grams, right? Really, it's this whole thing. Grams of water is going to cancel grams of water. And then in the top is going to be the energy unit that we're looking for, in this case, joules. And we know from the previous slide that water, or ice, I should say, absorbs 334 joules per gram in order to melt. Okay, so 32 times 334, this is 3 significant figures, right? This is 3 significant figures here. The 1 gram is considered to be exact, so we don't worry about that. So 3 times 3, our answer is going to be 3 significant figures as well. So in this case, 10,700 joules is 3 significant figures. Okay? You could also write this as 1.07 times 10 to the 4th power joules. Okay? You could also write it, since this is 10,000 and 1,000 joules is a kilojoule, you could also write it as 10.7 kilojoules. Okay? All of these are equivalent ways of writing this answer. If it's a short answer, you can pick any one. If it's multiple choice, you have to look for the one that's accurate, the one that you're given. Okay? So again, this is just looking at it as a conversion factor. If we looked at the formula, heat of fusion formula, right? Heat of fusion equals heat over mass. And then we want to solve for the heat, because the problem is how many joules. So we would solve for heat by multiplying both sides by the mass. And so we would get the heat equals the heat of fusion times the mass. Fix this a little bit. Right? And so this would be, again, 334 joules per gram times, in this case, 32 grams. But that's the same thing we got, 32 times 334. So it would give us the same answer, as it should, 10,700 joules. Okay? So there are 2 separate ways of looking at it. You can consider the heat of fusion to be a conversion factor, or you can remember the heat of fusion equation and put in your variables. So another type of phase change is boiling or evaporation. Okay? Boiling occurs when a liquid is heated up to the point that the molecules throughout the whole liquid have enough energy to convert into the gas phase. And since they can convert into the gas phase anywhere throughout the liquid, you'll start to form pockets of gas, and those are bubbles, right? So those bubbles will boil. Well, that is boiling. The bubbles will start to roil and come to the top, and that is the process of boiling. Okay? Evaporation is similar to boiling, but evaporation can actually happen at any time, at any temperature. But it only occurs near the surface of the liquid. So for instance, if you have an open glass of water in your room and you leave it there for a while, if you come back several days later, you may see that all of the water has evaporated, right? There was never 100 degrees Celsius in your room. It never reached the boiling point in your room. But nevertheless, the water at the surface of the cup of water, those molecules, some of them had enough energy to escape into the atmosphere, and once they were out, they never came back. And so over time, more and more particles escaped into the atmosphere, and this is evaporation, right? It happens slowly over time because there's a distribution in the energies of the particles, even when it's not at the boiling point. The opposite process to boiling is condensation. Right? And this occurs when the atoms or molecules in a gas lose energy and start to stick together. And so they coalesce and they come together and form droplets and condense back into the liquid state. And just like with melting, there's a specific heat associated with this phase change. Okay? In this case, we're talking about evaporation or vaporization. And so it's called the heat of vaporization. And again, just like with the other phase change, the heat of vaporization is the same as the heat of condensation, right? You're adding the heat in one direction and you're removing the heat, so adding the heat to go from liquid to gas and removing the heat to go from gas to liquid. But it's the same quantity of heat per gram in both cases, okay? So this is, again, you can come up with a similar formula to the heat of fusion. Heat of vaporization is heat divided by mass, the mass of the system you're talking about, and the heat that's required to vaporize it. Or if you're going the other direction, the heat that will be released when it condenses. Okay? So just like we saw, the heat of fusion for water is 80 calories per gram. For water, the heat of vaporization is larger. It's 540 calories per gram. So it takes more energy to vaporize a gram of water than it does to melt a gram of ice. Okay, significantly more energy. Okay? And again, if we're going to go in the other direction, we can take gas and we can condense it back into the liquid, and that will release the same amount, 540. Okay? The only thing that's different here really is the number, which corresponds to the heat of vaporization as opposed to the heat of fusion. And in this case, we're going from liquid to gas. And during condensation, we're going from gas to liquid. Okay? This G means gas. And again, we can express this as a conversion factor, 540 calories per gram of H2O, right? Whether we're talking about H2O as a liquid or H2O as steam, just as something we can determine from the context of the problem. And again, if we take this and convert it into joules, it's 2,260 joules per gram. So another similar question to what we got before, how many kilojoules are released when 50 grams or 50.0 grams of steam from a volcano condenses at 100 degrees Celsius? Okay? So it's energy that's being released because the steam has a lot of energy, and in order for it to turn into a liquid, it needs to get rid of some of that energy. Okay? As long as we're not worried about the steam or the liquid changing temperature, we're just interested in the phase change, then it's going to occur at 100 degrees Celsius. But again, that's not really necessary for the mathematics of the problem. But the same process is in place, right? So we start with what we know. We are given 50.0 grams of steam. We don't really care about the temperature. It's the boiling point or the condensation point, but we're not really concerned. It's just a little bit of context that we can keep in the back of our mind. And what we need is the number of kilojoules, the energy that's released when the steam condenses. So again, we should understand that converting mass to energy in this sense, or understanding the relationship between mass and energy, means using the heat of condensation. Okay, so we're going to start with the mass. We're going to use the heat of condensation to get to joules. And then in this case, it's asking for kilojoules specifically. So we're going to need to use a metric factor to get to kilojoules. Okay, so we'll be chaining two conversion factors together, right? This one and this one. So the first thing we can do is write down these conversion factors so that we know that they're available, right? The heat of condensation is 1 gram of water condensing from gas to liquid, releases 2,260 joules of energy, right? And so we can write it like this or like this. And then the other conversion factor we need is to just go from joules to kilojoules. We know that the kilo prefix means 1,000 or 10 to the third. So 1 kilojoule equals 10 to the third joules. And so we can write the conversion factor like this or like this. Which conversion factors we need depends on the problem, right? So in this case, again, we're starting with the mass of water. So this first conversion factor, we're going to want to go from mass. So we're going to want the same unit in the denominator to cancel out. And then we're going to want to go to energy, joules. Okay? And then, since the question asks for kilojoules, we want to have another conversion factor where we cancel out joules in the bottom and leave kilojoules in the top. Okay? So this will be our final unit. So 50 times 2,260 divided by 10 to the third gives you 113 kilojoules. Let me write it up here. 113 kilojoules of energy. Okay? This has 3 significant figures. This has 3 significant figures. This is considered exact. And both of these and the metric factor are considered exact. So these don't affect the significant figures. But since both of these other numbers have 3 significant figures, so will our answer. So 113 kilojoules. There is another phase change that's less common, but it's still interesting to learn about. This is sublimation. Sublimation is when you go from the solid phase directly to the gas phase without going through an intervening liquid phase. So atoms or molecules from the surface of the solid will basically jump off. They'll get enough energy to leave the surface of the solid and go directly into the gas phase instead of turning into a liquid. And then the opposite of sublimation is deposition, where the some gas particles can come back and they'll settle onto the surface of the solid and go back into the solid phase. Okay? So these are two opposite processes. You add heat to go from solid to gas. You lose heat to go from gas to solid. Right? You could associate a heat of sublimation or a heat of deposition with this process, the same way we did with freezing and boiling, but it's not as common, so we're not really going to concern ourselves with that, right? One place you might have seen this sublimation in practice is with dry ice. Okay? Dry ice is something that was used in movies in the past to give sort of a fog or cloudy appearance, right? Dry ice is actually solid carbon dioxide. So the carbon dioxide that we breathe out is a gas, but if you cool it down and pressurize it enough, you can turn it into solid blocks. But at room temperature, or really any temperature above minus 78 degrees Celsius, the dry ice, the solid block of carbon dioxide, directly converts into gaseous carbon dioxide. Okay? And in that process, it looks like it's smoking. So it looks like regular ice. The solid looks like regular ice, but if you just put it into a room at room temperature, it looks like it's smoking because the CO2 coming off it is very condensed at first. It has droplets, but it's turning into gas, and so it gets this smoky fog-like appearance. So that's why it was used in fog machines and things like that. So here we have what's called a heating curve. This one is for water in particular. A heating curve is basically a way of illustrating how the temperature changes as you change the heat or as you add heat. So here we have the temperature on the vertical or y-axis going up, and we have the heat that we're adding on the x-axis. So as we go from left to right on the x-axis, the heat that we're putting in increases. We're putting more and more heat in. So if we start with a solid water at negative 40 degrees Celsius, right, it has some energy. We don't really know what the initial energy was, but we're not worried about the exact numbers on the x-axis. But we have some solid water, otherwise known as ice, and it's at minus 40 degrees Celsius. As we begin to add some energy to it, the temperature increases, right? That's what happens. This is what we talked about during the specific heat section. Right? As you add energy, the temperature changes, temperature increases. And it increases until it gets to 0 degrees Celsius. 0 degrees Celsius is the melting point of ice. So at this point, when we continue to put energy into the ice, it no longer raises the temperature, right? From here to here, the temperature is the same. It stays at 0 degrees Celsius. But the energy that's being put into it, right, from here to here, we're still putting energy into it. The energy is going into melting it. It's going from the solid, which it is in this part of the curve, to the liquid, which it is on this part of the curve. Okay? And then once all of the mass of the ice has been melted into the liquid, then as we add energy, the temperature of the liquid again starts to increase, right, until we get to this point. So in this region, we're adding energy, and because now we're dealing with just liquid water and no phase change, the temperature changes, and so we have a delta T again, okay? Then once we increase the temperature to the boiling point, 100 degrees Celsius, then again we reach another flat plateau, right, where we put energy in, so we're putting energy in from here to here, but none of that energy is causing the temperature to change at all. It's all occurring at 100 degrees Celsius, right, until it gets to here, right? So the energy we put in between here and here goes into boiling the water, turning the liquid water into steam. Once we're here, then we can again begin putting energy back in, and the steam is going to increase in temperature, okay? So this shows you the relationship between the specific heat concept that we learned last time and the phase change concept that we learned this time. Both of them involve the addition of heat, right? Both of them involve going further to the right on this x-axis. But the specific heat occurs when you're dealing with one substance or one phase, and the temperature increases, so you get these sloped lines, right? And then the phase change occurs on these horizontal or flat portions of the curve where the temperature does not change. Okay. So again, these are simple conceptual questions. A plateau or horizontal line on a heating curve represents, well, it represents a constant temperature, right? Because if it's flat or horizontal, the temperature is not changing. And it's constant because it's a change of state. So it's both of these. And then a sloped line on a heating curve represents, well, the other part, right? It's not constant temperature because it's increasing temperature, and it's not changing state. It's really just a temperature change as you add heat. Okay. So if we look at the cooling curve, we can use that to answer some of these questions, right? But most of these we know pretty much from knowing the boiling and freezing points of water. So water condenses at a temperature of, let's see, water condenses at a temperature of, we're talking about condensation. So that means going from steam to liquid water. So that occurs at 100 degrees Celsius. At a temperature of 0 degrees Celsius, liquid water melts. Okay. At 40 degrees Celsius, water is what phase? Well, 40 degrees is above the freezing point or above the melting point of water, which is 0, and it's below the boiling point. Okay. So it's not a solid and it's not a gas, it's a liquid. And when water freezes, is heat added or removed? Well, the way to think about this is if you have water and you're turning it into from a liquid into a liquid tends to have more energy than a solid, right? That's why it's a liquid, because the particles have more energy. So if a liquid has more energy and you want to turn it into a solid with less energy, you have to get rid of some of that energy. So you're going to remove some energy from it. Here you see a cooling curve, which I'm not really going to talk too much about because it's really just the opposite of the heating curve that we just saw. The only difference is that in this case, as you go to the right on the x-axis, you're removing heat. Heat is being removed in this case. Okay? And so if you start from steam, you'll remove heat to decrease the temperature until you get to the 100 degrees Celsius. And then removing heat will cause it to condense at a constant temperature. And then you continue, now it's water, and as you remove heat, the temperature of the water decreases until you get to 0 degrees. And then as you remove heat, it'll freeze into ice at a constant temperature. And then after it's all turned into ice, as you remove heat more, the temperature of the ice will continue to decrease. So it's really just a mirror image of the heating curve. But it's useful to keep those curves in mind when we get a question like this, right? Because this question combines two concepts that we've dealt with already. The specific heat, which deals with heat causing a temperature change, and the heat of vaporization or condensation, which deals with heat causing a phase change. Okay, so this question says calculate the total heat in joules needed to convert 15.0 grams of liquid ethanol at 25 degrees Celsius to gas at its boiling point of 78.0 degrees Celsius. Ethanol has a specific heat of 2.46 joules per gram degree Celsius and a heat of vaporization of 840 joules per gram. Right? So before we get into the step-by-step way of doing this, again, it's useful to get in your mind some concept of this heating curve, right? So we're starting with ethanol that has a certain amount of energy, and it's beginning at 25 degrees Celsius. So if we put 25 degrees Celsius on our temperature axis on the left, and here we have our energy or heat axis, right? So we don't know what the energy is, but we're not really concerned with the starting energy. So we'll just say that we start at 25 degrees Celsius. And then we're going to be adding heat to it. And ethanol, in this case, we're talking about ethanol, not water. So ethanol is a liquid at 25 degrees Celsius. So as we add heat to it, the temperature is going to rise, right? But at some point, we're going to reach the boiling point of ethanol. And then when we add heat to it, the temperature is going to stay constant as the ethanol boils. So the question tells us that the boiling point is 78 degrees Celsius. So that means that this is 78 degrees. So there's two different sections to this curve that we need to worry about, right? There's the energy needed to increase the temperature from the initial 25 degrees Celsius to 78 degrees Celsius, right? There's this portion of the energy. And then there's this portion of the energy, which is the energy that boils the ethanol at 78 degrees Celsius, right? So we have this portion. So the total heat or the total energy needed to convert the 15 grams completely into the vapor phase is the combination of both of these parts of the graph. So we're going to need two equations to relate these, right? This is going to be specific heat, and this is going to be heat of vaporization, right? And luckily, they gave us both of these for ethanol because I don't know them off the top of my head. So, step by step, right? We're given 15 grams of ethanol at 25 degrees Celsius. Those are both important facts to know about this sample of ethanol. And what we want to know is the total energy, the total number of joules to heat this ethanol to 78 degrees Celsius, and then to convert it to gas at 78 degrees Celsius, right? So the first step is a temperature change from 25 to 78. And then the next part is no temperature change, but a phase change from liquid to gas, to convert it to gas. So we need two different things. We need to combine heat from the temperature change, which is specific heat here, and you can't see it, but it's a change of phase, which is in this case the heat of vaporization. Okay? So first, the liquid ethanol needs to be heated to bring it to the boiling point. Okay? So write a plan to convert the given quantity to the needed quantity. Think about the heating curve, right? The first step of the curve is that the liquid ethanol needs to be heated to the boiling point. So if we're taking a liquid and we're adding heat to it to increase its temperature, we're talking about specific heat. Okay? And then the hot ethanol needs to convert into gas, right? And so if we have a liquid and we're putting energy into it to turn it into a gas at a constant temperature, that's the heat of vaporization. Okay? So the total heat is going to be these two factors added together, joules to warm the ethanol and joules to vaporize the ethanol. So heating the liquid, we can use the specific heat formula, right? Specific heat, in this case, specific heat of ethanol, it tells us was 2.46 joules per gram degree Celsius, right? So we can think of that as a conversion factor, one of these conversion factors. And then boiling the liquid, we can just talk about the conversion factor of converting mass to the energy required. So 841 joules per gram. Okay, so these are the conversion factors that we're going to need. We'll need one of these and one of these, right? But which ones we'll need, we'll take a look at when we put them into the equation. So for the heating step, we need to calculate the temperature change, right? Because the specific heat formula, specific heat equals heat divided by mass times delta T, right? This delta T is the difference between the specific heat formula and the heat of fusion or the heat of vaporization formulas. So we're going to be going from 25 degrees Celsius to 78 degrees Celsius. So delta T is 78 minus 25, or 53.0 degrees Celsius. Okay? This is delta T. And so then we can just calculate the heat, right? We rearrange this heat equation. We rearrange it so that you have heat equals mass times delta T times the specific heat, right? So the mass is 15 grams directly from the problem. 53 degrees Celsius is the delta T that we just calculated, right? And then the specific heat from the previous slide, or what was given in the problem, is that it takes 2.46 joules of energy to increase the 1 gram of ethanol by 1 degree Celsius. Okay? So the 1 gram is considered exact, the 2.46 is 3 significant figures, 53.0 is 3, 15.0 is 3. So our answer is going to be the 3 significant zeros. 15 times 53 times 2.46, rounded to 3 significant figures, is 1,960 joules. Okay? So this is the energy it takes just to bring the ethanol from 25 degrees Celsius up to 78 degrees Celsius. Once we're excuse me, once we're at 78 degrees Celsius, then we need to know how much energy it takes to vaporize, right? So for this step, the heat equals the mass times the heat of vaporization as a conversion factor. And again, the heat of vaporization was given to us as 841 joules per gram. So 15 times 841 to three significant figures is going to give us 12,600 joules. Okay? So this is the heat just to vaporize. This is the heat needed just to boil or vaporize the ethanol, right? No temperature change is associated with this amount of heat. Okay? So if we want to know the total heat, the question asks for the total heat to go from the 25-degree liquid to a completely boiled or completely vaporized sample, then we need to take the first step and add it to the second step, and so we end up with a total energy of 14,600 joules, right, or 14.6 kilojoules, if we want to say it that way.